Snap a plastic stick and it begins to glow. No battery, no flame, no switch. Just a soft, steady light that pours out into the dark. It can burn for hours, then quietly fade away. Inside that little tube, a tiny chemical machine is already hard at work. Tonight, we slice one open and watch light get built from nothing but two clear liquids and a single careful reaction. Start with the body. The outer shell is a flexible plastic tube, sealed tight at both ends. It is already filled with a clear liquid, the first of our two ingredients. Because the plastic bends, you can squeeze and twist the stick without spilling a single drop. That flexibility is the whole point. It lets you trigger the reaction from the outside, while everything important stays locked safely within, waiting for the exact moment you decide to begin. Float deeper and you find a surprise. A thin glass tube hangs suspended inside the plastic one. This is the trick at the very heart of the design. The glass holds the second liquid, kept completely apart from the first. Two chemicals, one container, never touching. Glass is the perfect wall here. It is rigid, sealed, and easy to shatter on purpose. As long as it stays whole, nothing happens. The stick is loaded but silent. Now meet the cast. The outer liquid is mostly hydrogen peroxide, from the same family as the stuff that fizzes on a cut. The inner glass holds a different chemical, an ester mixed with a fluorescent dye. The peroxide is the spark, the ester is the fuel. The dye is the artist that will choose the color. On their own, each one is calm and harmless. Together, they are about to make light. They just need an introduction. Here is your part. You bend the stick. The flexible plastic flexes easily, but the rigid glass inside cannot follow. So it snaps cleanly into pieces. You feel the crack and hear a soft click. In that instant, the wall is gone. The second liquid, trapped for months on a shelf, is suddenly set free. Give it a shake, and the broken glass tumbles harmlessly inside. The two worlds, kept apart so carefully, are finally allowed to meet. Watch the two liquids swirl together. This is exactly why we shake the stick, to spread the chemicals evenly into every corner of the tube. The more thoroughly they blend, the smoother and brighter the glow. Down at the scale of molecules, peroxide and ester are now bumping into each other by the billions. Each tiny collision is a chance for a reaction. Multiply that by an ocean of molecules, and the stick begins, very gently, to wake up. Here is the first step of the chemistry. The hydrogen peroxide attacks the ester and tears it apart. Out of that break comes an unstable little molecule, a strained ring of carbon and oxygen that simply cannot last. Think of it as a wound-up spring, holding far more energy than it ever wanted to. It exists for only a flicker, then falls apart. But it does not waste that stored energy. It is about to hand the whole package to someone else. As that strained molecule collapses, it releases a burst of pure energy. But instead of escaping as heat, the energy jumps straight into a nearby dye molecule. The dye soaks it up. One of its electrons is kicked upward into a higher restless state. For a tiny moment, the dye is overcharged, holding energy it cannot possibly keep. Every glowing stick is really millions of these charged dye molecules, each one quietly loaded and ready to let go. Now the payoff, that lifted electron falls back down to where it started, and as it drops, it has to shed the extra energy somehow. So it spits out a single particle of light, a photon. No heat, no fire, just light born directly from a chemical change. Scientists call this cold light, or chemiluminescence. Billions of dye molecules doing this all at once is what your eye finally reads as a single, steady, gentle glow. But why green or pink or blue? That part is the dye's job. Each kind of dye releases its photon with a specific amount of energy, and that energy is the color. More energy leans toward blue, less energy leans toward red. Swap the dye and you swap the color, while the rest of the reaction stays exactly the same. The peroxide and ester are the engine. The dye is just the paint, deciding which shade of light pours out. Nothing lasts forever. Every photon spends a little chemistry, and slowly the ingredients run out. As they thin, the glow dims, and finally it dies. Temperature sets the pace. Warm the stick, and the reaction races, bright but brief. Chill it in a freezer, and it slows to a long, faint ember you can revive for days. Same light, same chemistry. You are simply choosing whether to burn fast and brilliant or slow and patient. So let us trace the whole chain. A flexible tube holds the peroxide. A glass vial inside guards the ester and the dye. You bend the stick, the glass snaps, and the two liquids finally mix. The peroxide breaks the ester into a strained, energy-rich molecule. That molecule collapses and hands its energy to the dye. The dye's electron leaps up, then falls, and releases a photon. The dye picks the color, and the cooling chemistry decides how long it all glows. No wires, no heat, just two patient liquids and one quiet reaction, turning chemistry into light in the palm of your hand. The next time a stick snaps to life in the dark, you will know exactly what is glowing inside it. That is the glow stick sliced open.